Okay, let's do some problems involving friction. I'm going to do 4, and I made these 4 up, and they're going to start off, and they're going to look at different things, but I'm going to do them all the same way. So you can practice, and that's the whole thing. You need to practice doing these a particular way. Don't just try to look for the solution. There's a method to solving these kind of problems. Okay, let's just jump into it. So I have a 2 kilogram block sitting on a surface, and it's being pulled up by a rope at a 20-degree angle. And so the mass is 2 kilograms. The gravitational force, the gravitational field is 9.8 newtons per kilogram. And then the coefficient of static friction is 0.4. That has no units. So the first thing that we need to know is that, and so the question is, what's the question? I didn't ask the question. The question is, how hard would I have to pull on this to get it to move? Okay, so the first thing is, if it's just about to move, then the total force on it's 0. And I know that seems kind of weird, but then if it just went a little bit harder, then it would move. So we're going to look at for the what force, tension force, would I pull such that I can get this to almost start to move. So we're going to use the following. We're going to say the net force on the mass is equal to 0. And that is a 0 vector. The forces are a vector. This is Newton's second law. This says that the net force is mass times acceleration, but the acceleration is 0. Okay, so I actually can write this as 2 other equations. I can say F net x equals 0 as a scalar equation. This says the total force is in the x direction is 0. And I can say F net y equals 0. The total force is in the y direction is 0. And it's a little bit easier to deal with these 2 scalar equations, than this 1 vector equation. Now the other thing is our model for friction. So friction, the magnitude of the frictional force, I'll just call it FF, lowercase f. This is the magnitude, not a vector, is less than or equal to the coefficient of static friction times the normal force. So what this says is that the maximum friction force, FF max, I'll just write it this one time, is going to be equal to the coefficient of friction times the normal force. Because imagine this, if I pull just a tiny little bit, there's going to be some friction force pulling back, but those forces have to add up to 0 because it doesn't move, right? And as I pull harder, then the friction force gets greater too. If the friction force was always at the maximum value and I pull it a little bit, the net force would be this way and the block would start accelerating that way, and I would freak out because that's weird. Okay. That doesn't happen. But we're trying to find the case where the friction force is it just starts to move. So we want this tension and we want to use the maximum friction force. And I know that seems a little bit weird, but that's where we're going to do it. Okay, so those are the things we're going to start with for every problem. The other important thing about friction is that it is parallel to the surface in such a way that it opposes the change in motion. So it doesn't want the 2 surfaces to slide. Let's start off with a free body diagram for the block. So I'm going to start right here, and I'm going to draw the block as a dot. And it just that way we don't have to worry about the dimensions of the block or the size. We will do that later, but right now we can just treat it as a dot. So what forces are acting on the block? Well, there's 2 kinds of forces. There's long-range forces, forces that can act on the block without touching it. And then there's contact forces that are due to something touching the block. The only long-range force that we have in this case is the gravitational force between the block and the earth, which is down here. So the gravitational force on the block is going to be this way, and I'm just going to write that as mg. So the gravitational force on the surface of the earth is the product of the mass and the gravitational field g. So I guess I should write g, the vector g is going to be 0, negative 9.8, 0 newtons per kilogram. So I like to write my vectors as this ordered pair between ordered triplets between angle brackets for the x component, the y component, and the z component. So it's pulling in the negative y direction. That's why it has a negative y component. Well, there's no other things touching the block, long-range forces on the block. So now we just want to look at what is touching the block. Well, there are 2 things. There's the surface, the ground, and the rope. Okay, so let's draw the rope. One of the things about ropes, and in fact, I have a rope. Here's a short little rope. And the thing about ropes is that they can only pull in the direction of the rope. I can't, if the rope is this way, it can only pull that way. If the rope is that way, it can only pull that way. Okay, and they can't push. It's just the way ropes work. So I know that there should be a tension in the same direction there. I'll call that T. Now what about the surface? The surface actually can actually have two forces acting on it. It can have a force pushing perpendicular to the surface. We call that the normal force. It's like this. And it can have a force parallel to the surface, and that would be the friction force. So if I'm pulling this hard, it wants to slide this way, so the friction force would be that way. So let's put it right here, and I'm going to draw it as a vector F, F. Okay, so those are I have 4 forces acting on the block. So the first thing is to identify the forces and draw a free body diagram. Got that. The next thing that we need to do is to choose an X and Y axis. So I'm going to pick my X and Y axis like this, because if I don't have an X and a Y axis, how can I do the net forces in the X and the Y direction? I have to know what that is. And this is not real, and you can pick this however you like. There are some directions that work better than others, but in this case, I'll just go ahead and pick that. So here's my x-axis, and this is that angle. I'll just leave this as theta for right now. Now we want to write these two equations out. We want to write all the forces acting in the x direction. So which of these forces act in the x direction? Well, the normal force is only in the y, and the gravitational force is only in the y. So they don't have an x component. The friction is in the negative x direction, and the tension is in both the x and the y direction. So we'll need to get the x component of the tension. So if I draw a little triangle right here, this side is the x component of the tension. And you'll notice that if this is the total tension, this would be the adjacent side. So if I say cosine of theta is adjacent, I'll call that tx over t. Then tx is going to be t cosine theta, where t is the magnitude of that tension. Okay, so we can write down the net forces in the x direction now. I can say F net x is going to be equal to the component of the tension, which is going to be T cosine theta, and we do know theta, but we're just going to leave it as that. And then I have the friction force in the negative x direction, so it's going to be negative F, and those have to add up to 0. Now let's do the same thing for the y direction. In this case, there are 3 forces that have a y component: the normal force, the gravitational force, and part of the tension. And so now we're looking at the y component of the tension, which is right here. So that would be T sine theta, would be this y component. We can do the same thing by saying sine theta is opposite of hypotenuse. So I can write down F net y as N, the normal force, plus T sine theta. This is the y component of the tension. And then I have the gravitational force in the negative y direction, so it's negative mg. And those have to add up to 0. You'll notice something very important here. If I'm pulling on the rope, so there's some value for t, this is not a 0 number. This number is not 0. So there's no way that N minus mg can be 0. So N is not mg. I'm going to put that off to the side. N not mg. So there's so many problems. There's so many problems that you come up with that the normal force happens to be equal to the weight. And I just want you to be careful and not try to put it as always true. It's not true in this case. Okay, because if you think the normal force tries to prevent the block from falling through the table, and so it pushes up as hard as it needs to. It doesn't need to push up all of the gravitational force because tension's pulling up some too. It gets a little help. Okay, so the normal force is smaller. So now I have 2 equations, and I'm trying to solve for the tension. So I don't know the tension, I do know theta, I do not know the frictional force, I do not know the normal force, I don't know the tension force. So I know everything here except for 3 things, but I only have 2 equations. So I need another equation, but I actually have one up here, so let me just write that right here. F friction equals mu s times n. So I do have 3 equations, 3 unknowns, and I can solve it. So let me get, where am I? I had some paper. Here it is. Okay, so let's just jump to another piece of paper, and I'm going to write those three equations. Actually, I'm going to go ahead and substitute this. Instead of friction force, I'm going to say mu s times n. So then I'll have just two equations. So my two equations will be this. Here's my new x equation is going to be t cosine theta minus the coefficient of static friction times the normal force is equal to 0. And then I have n plus t sine theta minus mg equals 0. So now I only have two things that I don't know. I don't know t and I don't know n. I don't know n, I don't know t. So again, I need to solve one of these for one of the variables and substitute into the other. I care about t. So let's solve this for n. So I'm going to add mg to both sides. If I do the same thing to both sides of the equations, that's fine. And then I'm going to subtract t sine theta from both sides. So now this equation becomes n equals mg minus t sine theta. Now up here I have an n. I can substitute this in. This n. Get it? I can substitute the n in. It's a little physics humor for you, just to kind of, help things move along. Okay, so now this equation becomes this, t cosine theta minus the coefficient mu, that's a Greek letter mu, I say mu, times all that n stuff, I'll put it in parentheses, mg minus t sine theta equals 0. So now that's an equation I can actually solve. You could put in your numbers, but I'm not going to put in the numbers just yet. So I want to get the t's together. So to do that, I'm going to multiply the coefficient through. So this becomes t cosine theta minus mu s mg. Now I have a minus mu s times minus t sine theta, so I get plus t mu s sine theta equals 0. And so now right here, I can combine these two terms and factor out the t. So this is going to be t cosine theta plus mu s sine theta minus mu s mg equals 0. Now I can add this to both sides. I get t cosine theta plus mu s sine theta equals mu s mg, parentheses. And now I can divide both sides by this, and I get t equals mu s mg over cosine theta plus mu s sine theta. I don't need to put that in parentheses. And that's my answer. Now, and I know all my values, but let me just check real quick. This should be in units of newtons. So let's check the units. This says mu has no units. M times G is units of newtons. Cosine theta, no units, no units, no units. So I do get units of newtons. That's good. We could also check the cases. What happens as the angle goes down to 0? As the angle goes to 0, sine of 0 is 0, cosine of 0 is 1. So I just get, yeah, that's 0. So I just get mu s times mg, and that's the maximum friction force without pulling up. So that works. Okay, let's go ahead and put in our numbers. T equals mu. I had mu as 0.4. I'm not going to put my numbers, my units in. The mass was 2. G, that's the magnitude of G, so it's 9.8 over the cosine of 20 plus 0.4 times sine of 20. Now this is a great chance for you to practice putting things in your calculator. I'm going to use this calculator, even though I don't really like calculators, but I'm going to do it anyway. So just be careful about order of operations and be careful about degrees. So I am in degrees mode, it says right there. Okay, so I'm going to enter the top end first, 0.4 times 2 times 9.8 divided by. Now here, I need to be careful because I'm going to have a sum on the bottom, so I need to put a parentheses. So I can say cosine 20, cosine 20, close parentheses, plus 0.4 times sine 20 close parentheses. Now I need another close parentheses for the bottom for the denominator, and then I can press enter. And I get, what's that? 7.28 newtons. Okay, let's do another problem. I could make these separate videos, but I really don't want to. I just want to do the problems and have fun. Okay, so let's do this problem. I have the same block. So it's still the same thing. I still have mass, 2 kilograms. Mu is mu s, static friction, 0.4. So let's do this classic problem that's related, but it'll show something important. Suppose I put this on an inclined plane like that, so it's a wedge. And I want to know at what angle theta it will start to slide. So again, the first thing we need to do is to say, well, what are my forces? I need to draw a free body diagram. So I'm going to start right here with my dot. And I have one long-range force. I have the gravitational force pulling down, mg. Now, what's in contact with the block? And it's just the wedge, the plane. So I can have two forces from that. I can have a normal force, which is normal means perpendicular. So the normal force is indeed this way. It's not up. It's perpendicular to the surface. And the friction force would have to be parallel to the surface, and that would be this way. So those are my three forces. The next thing I need to do is to choose my coordinate system. Now, you can pick anything that you want. As long as x is perpendicular to y, it will work. However, if I pick, I have a lot of experience. So if I pick this as x and this as y, I get a bonus. And the bonus is that the normal force is only in the y direction. The friction force is only in the x direction. But I do have components for the gravitational force. So, but this way I only have components of one force. If you pick x is this way, y is that way, then both friction and normal force will have to have components. And I don't want to have to do that because I'm lazy. And that's fine. And you can't stop me. Okay, so we need to find this angle right here. So let's just draw, here's the gravitational force. I want to find that angle right there. Well, if you think of this as a right triangle, that angle's theta. I'm just doing a little geometry here. That angle's theta. All the angles add up to 180, so this is the complement of theta, right? Because that's 90, so that has to be the complement of theta. And then this is 90 degrees, so that has to be the complement of the complement, so that's theta. So this angle is theta. That comes up all the time in these kind of problems, so just get used to it. That's fine. Okay, so now we need to write down our force equation. So let's start with the x, F net x. So what forces are in the x direction? And this is my x direction now. So is the normal force in the x direction? No. Is friction? Yes. Is gravity? Yes. A component of the gravitational force is in the x direction. So if you look at it right here, that's the x component of the gravitational force, and that will be the y component. And that's the opposite side of this right triangle. So if I take the sine of theta, I get the x component over the hypotenuse mg. So that means that the x component, I'll go ahead and write this as is going to be mg sine theta. That's the x component. So be careful, right? Don't always say the x component is cosine. That's not true. And then I have the frictional force in the negative x direction, so that's going to be minus FF. And this has to be equal to 0. Now let's do the same thing for the y direction, F net y equals. So now I have, in the y direction, I have the normal force in, and then I have the y component of the gravitational force. In that case, is the adjacent side of this triangle, so it's going to be cosine. It's going to be minus mg cosine theta equals 0. Okay, so I still have the problem that I don't know theta, and I don't know F, and I don't know N. That's three things I don't know. So let's eliminate the friction force by saying the friction force is equal to, because we're at the maximum case right before it slides, mu s times n. And then if I put that in up here, I get mg sine theta minus n equals 0. That's this equation. Wait, mu s, sorry. My mistake. That's right. So now what I want to do, let's go ahead and solve this one for n and plug it in up here. So if I solve this for n, I can add that to both sides. I get n equals mg cosine theta. And if I put that into this equation, I get mg sine theta minus mu s mg cosine theta equals 0. Let's add this term to both sides, and I get mg sine theta equals mu s mg cosine theta. Now I can divide both sides by mg, and that cancels. And so I want to find theta. So let's do this. I have sine theta on this side and I have cosine theta on that side. Let's divide both sides by cosine theta. So I get sine theta divided by, this is a little trig trick for you. Cosine theta equals mu s. And so now I can use my trig identity that sine over cosine is tangent. So this is going to be tangent theta equals mu s. And now I just need to solve for theta, and I get by taking the inverse tangent on both sides, theta is going to be the inverse tangent of mu s. So let's put in my values. It's going to be inverse tangent of 0.4, and now I can put it in my calculator. It's already in degrees, so I'm going to say tangent inverse 0.4. Can you see that? There you go, that's better. Close parentheses, enter. And I get, what's that, 21.8. It says 2.1 times 10 to the 10 to the first. So theta is 21.8 degrees. Oh, we should stop. No, we shouldn't stop. Let's do another problem. I said I was going to do 4. I'm doing 4. I mean, you can stop the video, okay? But I'm not going to stop the physics. Why? Because I like physics. Okay, so here's a fun problem. Same block, but now I have a vertical surface, and there's my 2 kilogram block, same coefficient, m is 2 kilograms, mu s equals 0.4. Again, I just made that up. So if my block is up against a wall, one thing I can do is to push with my finger. And if you push hard enough, you can get it to stay. And so the question is, how hard do I have to push on that block to make it stay? So this is a fun problem. Let's, again, start with the free body diagram. So I want to identify what forces are acting on it. Well, yes, I do indeed have a gravitational force. There's a gravitational force pulling it straight down. That's my long-range force, mg. Now, what's touching? Well, the finger's touching, right? The finger's pushing on the block, so that'll be this way, Fp. I'll call it for the push. What force is pushing up and what force is pushing this way? Well, the wall is a surface. It exerts a normal force that's perpendicular to the surface. So perpendicular to the surface would be this way. So there is a normal force this way. The normal force is not equal to mg, not even in the opposite direction. And then I need something preventing it from sliding down, and that is the friction force, Ff. So this is nice. We need to pick our x and y axis. I hope that you would pick this. But if you don't, if you pick some other direction for your x and y axis, I will respect your decision, and I salute you. Okay? But if you pick this way, then all these forces are either in the x or y direction, so it makes it pretty easy. Now we can do F net x. What forces are in the x direction? We'll have that, Fp, P, and then I have the normal force minus n, and that equals 0. What forces are in the y direction? F net y. Well, I have F friction minus mg. And I want to solve for Fp, but I don't know Fp, I don't know n, I don't know the friction force. So again, I can say Ff equals mu s times n. If I put that in down here, I get mu s n minus mg equals 0. So let's solve this for n and put it in up here. So I'm going to add mg to both sides. Mu s n equals mg. I'm going to divide both sides by mu s. N equals mg over mu s. And then I can substitute that in up here. I get fp equals, fp minus mg over mu s equals 0. So I can add that to both sides. fp equals mg over mu s. Now we can put in our values. 2, 9.8 over 0.4. I don't know why I put that in parentheses. I just felt like it. So put it right here. 2 times 9.8 divided by 0.4 equals, what does it say? 49. That's that. That was fun, huh? Okay. I'm having fun, so we're going to do one more problem. If you need to take a break, take a break. I mean, it's YouTube. It's a video. You just press pause and you come back. It's not a big deal. Okay. I'm not going to take a break. Okay, so it's the same thing. But now, what if I push up at some angle, and let's call this an angle of 20 degrees. So that's my finger. I'm pushing up at an angle like that. Okay. So how hard do I have to push now? I guess I should draw that as a vector. So again, we're going to identify the forces. It's actually the same forces. We have the downward gravitational force. We have the finger pushing this way. We have the friction force is up. And then we have the normal force is that way. And that might look a little familiar. That's fine. In that case, this, let's see. Yeah, this is 20 degrees. So let's just call that theta. Because I'm going to give you a bonus problem that you can work on. So now I can say this is my x and y axis. Again, if you want to pick something else, I salute you for your choice in making things more difficult. Because sometimes it's just fun to make it more difficult, right? So if that's the case, I can say F net x. What forces are in the x direction? Well, I have part of this finger pushing force, and that would be this side of the right triangle, right? So it's going to be cosine. So I have Fp cosine theta, and then I have minus n, because the n's in the negative x direction, and that equals 0. Then I have F net y is going to be equal to, I have the friction force pushing up. I have the component of the push force, which is this opposite side of that triangle. So it's going to be plus in the positive y direction, Fp sine theta. And then I have the downward pulling gravitational force minus mg. Again, I have 3 equations, 3 unknowns, but F friction equals mu s times n. And again, just a reminder, this is only for the maximum friction. And we're trying to find the minimum force, so you don't want the maximum amount of friction to help push it up. If I put that in down here, I get mu s n plus Fp sine theta minus mg equals 0. And I want to solve for Fp. So I'm actually going to solve this one for n and then substitute n down there. So this one becomes adding n to both sides. I get n equals, and flipping the order, Fp cosine theta. And then I put that in down here. I get mu s Fp cosine theta. I don't know why I put that in parentheses. I just felt like it. Plus Fp sine theta minus mg equals 0. I can add mg to both sides and factor out the Fp. So I'm going to do both those in one fell swoop. So I get Fp times mu s cosine theta plus sine theta equals mg. Now I can divide both sides by this. Fp equals mg divided by mu s cosine theta plus sine theta. And let's put in our values. I have mass of 2, g is 9.8, mu is 0.4, cosine of 20 plus sine of 20. And let's put it in the calculator. Okay. Can you see that right there? Okay. So I have 2 times 9.8 divided by parentheses 0.4 times cosine 20, close parenthesis, plus sine of 20, close parenthesis. And then one more for the whole denominator, equals. And I get 27.3. And just as a comparison, I mean, if it's a mg is 2 times 9.8, right? So that's going to be equal to 19.6. So if I just want to hold it up in my hand, that's how hard I'd have to push. I actually have to push harder than that to keep it up. Now, for the fun problem, and you can kind of use this. What if I push straight? I did that one, right? I push with 49 newtons. Same block. If I push at an angle, I push with less. What if I push at 21 degrees? Would it be greater than or less than 27.3? And in fact, I don't even know the answer. But I do know that there is some angle that you can push the minimum amount. And that's a fun problem to think about. What angle can you push the least and keep the block up against the wall? And could it ever be less than the gravitational force? That's something to think about. Okay, so that was 4 problems. I told you I'd do 4. I did 4. 4, count them. See? 4 problems using friction and free body diagrams to help you practice. Hope that helps.